So 4.2, and really this whole chapter, okay, is triangle congruence. How are these two triangles congruent? So we're going to be looking at two different triangles for pretty much everything we do in this chapter. How is this triangle congruent to this triangle, okay? And so far, what we did yesterday was we said all three angles of this triangle have to be the same as all three angles of this triangle, and all three sides of this triangle have to be the same as all three sides of this triangle. Today it changes. So today we're going to talk about two different congruence theorems where you don't need 6 things anymore. You need 3 things. It's beautiful. So the first one is called SSS, which is really just short for side, 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 okay? You never need to write side, side, side. You may write SSS every single time. And what the SSS postulate says is if the 3 sides of one triangle are congruent to the 3 sides of another triangle, then the triangles have to be congruent. So if you know the 3 sides are congruent, there is no way to make a triangle with those exact same 3 sides that has different angle measures. It's not possible. So I'm just going to draw it for you. If you want to write it out in words, you are welcome to look it up and write it out. But I feel like this does the job. So if I have these 2 triangles, where this is ABC and this is DEF, okay, as long as I know that AB is congruent to DE, BC is congruent to EF, and AC is congruent to DF, okay, so side, 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 right? 3 pairs of matching sides. As long as I know that, I can say triangle ABC is congruent, and then you have to make sure you match up the corresponding parts. So if it's ABC on the first one, what does it have to be on the second one? DEF. So I went from 1 hash mark to 2 to 3, so you got to do that all the way around for the second one too. Okay, so that's the SSS postulate. The reason that works is triangles are what we call rigid figures. If I have a triangle, so say this is my triangle, and I push on the top of that triangle, when it moves, you can't keep them together. Like if you were to push on that side, it's just going to move down the other side. It's not going to shift the whole triangle. So you just can't have 3 different lengths and still keep the angle measures. Like a rectangle is not considered a rigid figure. If I push on the top of the rectangle, I can make a parallelogram out of it, right? But a triangle is a rigid figure. You can't just shove a little bit and make some new triangle. So that's why side, side, side works out, because the 3 lengths have to make the same triangle every single time, okay? So we're going to do a proof using SSS.
Are there any other groups that are any groups? This triangle? Because with all others, then you could change angle measures, right?
Yeah, but you can change, like even on a non-rigid figure, like a rectangle, your angle measures change. It's just that you can still keep all the pieces connected, right?
Yeah, but are there any other figures that do it like triangles? Like where you can't move the angle measures without the pieces being unconnected?
That's a good question. I don't think there are. I don't know. I'll have to look it up. But I don't think so. All right, here it is. Let's say you are given that LM is congruent to NP and LP is congruent to NM. And we want to prove triangle LMN is congruent to triangle, oh, no, that's not right, triangle NPL. Okay, so I'm going to draw you a picture. This is P, N, M, and L. Okay, so my advice to you, most of the time, whatever is given gets marked for you, but just keep in mind, it's a really good idea every time you get a new proof to mark the given information. If it's marked for you already, great, then that's less work to do. But if it's not marked for you, make sure you mark it. So LM congruent to NP, that would be this segment congruent to that. So top congruent to bottom. And then LP is congruent to NM. Okay, now yesterday we would have had to say a third side is congruent to a third side and then prove all three sets of angles congruent. Well, right now we have no information that proves any of our angles congruent, right? They didn't tell us lines were parallel, so we can't do alternate interiors. So there's no way we're gonna do triangle congruence definition, right? Where we say all 6 things are true, which is why there's beauty in having a shortcut. And our shortcut today is SSS. So if we need a third side to be congruent, is there a way for us to prove the third side of both of those triangles are congruent? Do you see it? I know you do. I want to give everyone a chance to see it first, though. What is it, Daniel?
The reflexive property.
It is the reflexive property. Okay, here's another pointer for you. When you see 2 figures, 2 triangles that match up on a side, the reflexive property is going to be there. Okay, so let's just start the proof and we'll get to that reflexive property. What is number 1?
Given.
Always the given. Okay, so this is going to be given. And I would, if I were you, if you wrote this stuff out, I would just do this. For the sake of your homework, because you maybe aren't writing all the given information out, that's okay. I don't really care about that so much. If you give me given here, I am totally fine with you doing a squiggly mark here like you wrote all the given stuff in, okay? I'm not trying to create more work for you. I just want to make sure you get it. So you can totally do that. Yes, sir. On a quiz or a test, you'll have the given information written there so you can put a circle around it and draw an arrow in. Typically, I give you that stuff anyway, written in, which is another reason I'm not real picky about you writing it all out. Okay, so we know the given information. The next thing we need to say then is that LN is congruent to LN. And then mark that because it helps you to see once you mark LN congruent to LN by what property?
The reflexive property of congruence.
By the reflexive property of congruence, which you may just write reflexive. Then once we have that, what do you see in all your markings?
That they all have the same, all of their sides are congruent to each other, so you can use the SSS to say
Right.
they're
So if we have all 3 sets of sides match up with all 3 sides, then we can say the triangles are congruent. Triangle LMN is congruent to triangle NPL by SSS.
Could you also say the definition of congruent triangles?
No, because the definition of congruent triangles is all 3 sides and all 3 angles congruent. And we didn't prove all 3 angles congruent. Okay, here's my next pointer for you. When you see triangle congruence as your step, triangle something congruent to triangle something, it will always be SSS or one of the other 3-letter postulates that we're going to do. So there's SSS, SAS, ASA, AAS, and then there's HL, which is only 2 letters. It will always be one of those 5 when we say triangles are congruent. Okay, so keep that in mind when it says triangles are congruent, you need a triangle congruence postulate, okay? Okay. The next one that we're going to talk about uses a word that we need to define before you can move on. It talks about the included angle. Okay, and I'll get to what the postulate actually says. But the included angle in a triangle is the angle that's between the two sides that we're talking about. So if I'm talking about triangle ABC here, and let's say I know that AB, let's do this actually. Okay, we're gonna say we got two triangles. I'm not gonna worry about letters for the other one. So I know these are congruent and I know these are congruent. What we need is called an included angle. And think about what it means to be included. You're with someone, right? If you're included. So the included angle is the angle that falls between those two sides that we know. So in this picture, this would be the included angle, right? It came between the two sides. Okay, B is not included, C is not included, A is the included angle. Does that make sense? So it's gonna fall, it's gonna be formed, the angle is formed by the two sides we're talking about. Okay? So we are gonna use then, a second shortcut that uses the included angle. And our second shortcut is this, it's called the SAS postulate, which is side, any guesses what our A is?
Alter.
Nope. Look up here.
Angle.
Angle. It's side, angle, side. Okay, so the SAS postulate says if you have two sides in the included angle of one triangle that are congruent to two sides in the included angle of another triangle, then those two triangles have to be congruent. There is no way to come up with a triangle that has SAS congruence that is not congruent, okay? So your picture of what that would look like would be this. You have so if this is A, B, C, and H, I, and J, and I tell you that AB is congruent to HJ, and I tell you that BC is congruent to HI, and I tell you that angle B is congruent to angle H. Okay, they have to follow the same order. They have to both be the included angle. So in this picture, I have, and some people I found like to do this. If this is you, great. If it's not, totally fine. But they'll mark it just because sometimes you're going to learn more theorems. Like one is ASA instead of SAS. And a lot of times people call this ASA because you just think alternating. Oh, my letters are just alternating, so ASA. But it's not an angle, a side, and an angle. It's a side, an angle, and a side. So if you want to put S's and A's in to help you remember which one's which, you can totally do that. Don't have to, but if you want to, you can. So this would be side, angle, side as well, which means which two triangles are congruent. If I say triangle ABC, which triangle is that congruent to? JHI. Okay, you have to match up the corresponding parts. And I'm just giving you like the basic setup where you see it in the same order. But remember, things can flip, things can turn, things can slide, and you can still have SAS congruence. Questions on that one? Okay, so let's say I give you an example 2 here. Well, we asked the question, what other info do you need to to prove triangle DEF congruent to triangle FGD by SAS. Okay, and here's our picture. That didn't work. All right, so here's the deal. Based on the markings given, if you look at the two triangles, right now one thing was marked for us, right? We have one side congruent to one side. What else do we know in this picture is congruent?
FD.
Right, so even though it's not marked, we know the reflexive property is true. So even though this isn't marked, we know FD is congruent to FD. So we don't want to say that's information we need yet because we already know it. But if I want SAS, I need one more piece of information. What angle would have to be congruent to what angle to make this side angle side with side angle side? Matthew. Right, so angle FDG, that's this angle, would have to be congruent to this angle because it has to be the included angle, right? It has to be the angle between the two sides. So you would have to say, in order to prove these two triangles congruent by SAS, we'd have to know that EFD is congruent to angle GDF. Okay, so when they ask you what other piece of info you need, don't give the thing that you know to be true because of like the reflexive property or something like that. Give the thing that we don't know is true yet because they didn't tell us these lines were parallel, right? So they're not alternate interior angles that have to be congruent. We would have to know they're congruent to be able to say SAS. Yes.
How would you be able to
An included angle doesn't prove anything for you. Like if you need to show those are congruent, usually it's going to be by alternate interior angles on that. But you can't do it by an included angle because that doesn't prove they're congruent. You need to prove they're congruent, which in this case, they would have had to tell us the lines were parallel. But yeah, you'll never say included angle on a proof. It doesn't prove something to you. It's just telling us which angle we're looking at. Does that make sense? Okay. Okay, here, what I'm going to give you right now, you're going to see a lot of on your quizzes in the next several days. So just take a look at these, see if you can determine what theorem or what postulate is being used. All right, the question is, would you use SSS or SAS to prove the triangles congruent? And then if there's not enough info to do either, you're just going to write NEI. Okay, so another 3 letters, right? Not enough info. So you're either going to say, yes, they're congruent, and here's why, SSS or SAS, or you're going to say, I don't have enough information to be able to tell. So then NEI, okay? So let's say our first picture looks like this. And don't say it yet. I want to give everyone a chance to draw. And then we'll look at it. All right, so if you look at those 2 pictures, is it SSS, SAS, or NEI? Who thinks it is SSS? Who thinks it is SAS? Who thinks it is NEI? Good. So you have a side, the included angle, and a side, the included angle, and a side, so that is SAS. Notice it flipped, right? It flipped over, that's okay. It can flip and still be SAS, okay? How about this one? If I give you this setup, SSS, SAS, or NEI, who thinks SSS? Who thinks SAS? Who thinks NEI? A lot of you didn't vote. It is NEI. Do you see why?
Yeah.
This first triangle, you have side and side. This is your included angle. So side, angle, side, right? This one, you have a side and a side. This one would be the included angle. This one is not. This one we call the donkey theorem. I'll let you figure out why. So we would say this is not enough info, okay? Just so we're clear, the donkey theorem never works, so you never get to swear at me, okay? If you ever write the word ass on your paper, you're wrong. Don't do it. So we'll get more into donkey later because there is a donkey theorem that works, but we no longer use A's and S's for it because it's a unique triangle. So you'll see what I mean by that in a few lessons. But I always just tell people, if you ever feel like swearing at your teacher, you're wrong, right? You don't want to do that. That holds true with this. Do not put ASS, or even reversing that, SSA, does not work as a theorem. So if you ever get it where you think, oh, it's ASS, think, nope, not supposed to swear. I obviously can't do that, okay? It's just, it doesn't work as a theorem. All right. How about this one? Sorry about the disjointed triangle. Based on markings, not my terrible drawing, what would this one be? That is SSS. You have a side with a side with a side, right? So SSS would work here. So you would say SSS. Okay. How about this one? One of these days I'm gonna get the Apple Pencil and an iPad that's compatible with it. It's gonna be awesome. So I don't have squiggly lines everywhere. Okay, so this one's kind of a trick question. Not a trick question. There are options for you. Does anyone see what your options are right now? Right, you can use either SSS because you have your three sides, or you can use SAS. Why can you use SAS? Yeah, Matthew. Because of vertical angles. So even though this isn't marked for you, you know that it's true. So even though it's not marked, you may mark it because we know that vertical angles, remember in chapter 1, I think it was, we said you don't need markings to know vertical angles are congruent, right? So even though it's not marked congruent, we know it's congruent. So you may mark it and you may use it, okay? So that one could be either. Any questions on those? That is SSS and SAS. Yeah.
Does it matter which one we use?
No, you can use either one. Okay, just one last thing. I said it already. I'm just repeating, but hear me on this. When your last step of a proof says triangle ABC congruent to triangle DEF, what are you going to put here?
Either the definition of, not the definition of congruent triangles, you can put SSS or SAS.
Right. So whenever you are proving triangles congruent, it is always going to be SSS, SAS, or I'll just give you the other ones you're going to learn, but we haven't learned these yet. Okay, and I will say that to you over and over and over again. You'll hear me say it more. But just get in the habit. If you're proving triangles congruent, it's going to be one of those 5 every single time. Okay? And it's usually the last step of your proof. As we get a little further into the chapter, we'll do one where it's not the last step of your proof. But majority of the time, always right now, in this lesson, it's always going to be your last step. Okay? Questions on that?